The design of a spinning object such as a yo-yo should have the proper mass distribution and balance to assure smooth operations with minimal vibrations or wobble. Simple yo-yo designs may have perfectly symmetric halves and experience little to no out of balance issues. But what about more complicated designs? If the yo-yo is designed or even assembled with unsymmetric mass balance, when the yo-yo is spun, it may oscillate or wobble. In this video, we'll show you how to virtually simulate a spinning yo-yo on a string and investigate some what-if changes to the design and how those changes affect the yo-yo's spinning behavior. Ready? Let's go. Our goal is to simulate the spinning of a yo-yo to check its dynamic behavior, with the intent to identify any predicted oscillations, wobbles, or even gyroscopic precession due to the mass distribution. The location of the center of mass with respect to the spinning axis and the attachment point of the string, as well as the orientation of the principal axes of inertia with respect to the spinning axis, are important measures that will govern the dynamic behavior of the spinning yo-yo. These mass properties can be computed before the simulation, and then the dynamic simulation can be performed quickly to visualize and understand the effects of varying mass distribution. During the lesson, we will illustrate our general dynamic setup and these concepts. We'll also walk through step by step how to simulate several conditions with our simple yo-yo. For this lesson, we will use the Ansys Rigid Dynamic Solver. While this solver is called a rigid dynamic solver, it can include elastic deformations, but we'll just be treating our yo-yo as rigid parts, and we'll be solving for the kinematics of the yo-yo, not any elastic deformations. If we wish to solve for elastic deformations, we could include them using special techniques or using a finite element based solver in Ansys Mechanical, such as the transient structural. Since we treat the yo-yo parts to be rigid and fixed to one another, the yo-yo will have only 6 degrees of freedom, 3 translations, and 3 rotations, so the simulation is extremely fast. Okay, let's get into Ansys and get started. Open Ansys Workbench. Now drag and drop a rigid dynamic system into the workspace. To perform this simulation, we will go through each of these cells from top to bottom and complete each one of them. Double-click on Engineering Data. This list shows all the materials that we can use in our simulation, and structural steel is present by default. Let's say some portion of the yo-yo are made of polypropylene, so we need to define properties for this material. To do this, click on Engineering Data Sources, answer Grantum Materials Data, and then choose Polypropylene Plastic from the list. Click on the plus sign next to it. Now, when we click on Engineering Data Sources again, we see that polypropylene plastic has been added to the list of materials that we can use in our simulation. Close the Engineering Data tab to go back to the project workspace. The next cell we have is Geometry, which means the next step is to import the CAD geometry. To do this, right-click on the geometry cell and choose Import Geometry. Then go to the relevant file location and select the geometry file. You will notice that as each cell is completed, the symbol changes to a green tick. To complete the next 4 cells, we need to open up Ansys Mechanical. So double-click on the model cell. Now we are in Ansys Mechanical. Before we start setting up the model, let's go to Units under the Home tab and make sure it's set to metric system with millimeters, kilogram, second. On the left we have the tree outline, and similar to the cells in the Workbench project, we complete each item here from top to bottom. Let's take a look at the different components in our assembly. Go to the Display tab and then under Explode, move the slider to the right to see the exploded view of the assembly. The yo-yo has 2 halves connected to each other by a spacer. Each half has a body, a cover, and a snap ring. We need to define the material for each component. First, let's select the spacer. In the Details window, we see that structural steel has been defined as the default material. Let's leave this as is. For all other components, we will assign the polypropylene plastic material. To select multiple components at the time, press Ctrl and choose all the components except the spacer. In the details, change the material assignment to polypropylene plastic. The next step is to define how different components interact with each other. In real life, when 2 bodies come in contact, they exert contact forces on each other. In simulations, however, we explicitly need to define the interaction between two contacting bodies. Otherwise, they will simply pass through each other. We can define these interactions either through contact or through joints, which are defined through the connections option. When a mechanical assembly is imported in Ansys Mechanical, contact pairs are auto-detected and defined as seen here. However, in our case, we will delete these auto-generated contact pairs and define fixed joints between various components, since we assume that relative displacement or rotation between the components is 0 in our design. So let's go to Connections, Insert Connection Group. Under the details of the connection group, change the connection type to Joint. We only want to define fixed joints, such that the two components connected by a fixed joint will have 0 relative displacement and 0 relative rotation. So under Auto Detection for the revolute joints, select No. Now, right-click on Connection Group and select Create Automatic Connections. We see fixed joints are now created between the different components. Now we'll need to model the string attached to the yo-yo. We'll use a nonlinear tension-only spring which provides resistance under tensile forces but has 0 stiffness under compressive loads. Right-click on Connections, Insert Spring. In the Details window under Definition, let's set the spring behavior to tension only. Let's define the longitudinal stiffness and the longitudinal damping. Our spring is nonlinear to represent a string which can carry a tensile load but not a compressive load. We specify a small amount of damping in the string to account for the energy loss in the stretching of the string. Let's set the scope to body ground since one end of the yo-yo string is attached to the yo-yo, i.e. the body, and the other end of the string is stationary and hence can be denoted by ground. In the reference, let's put a reference Z coordinate of 100 millimeters. Under mobile, select the outer faces of the spacer. Next, we define a general joint between the ground and the spacer. The general joint permits us to selectively choose which degrees of freedom are free or fixed and allows us to apply the rotational boundary condition on the yo-yo, which we will discuss in a few minutes. So right-click on Joint, Insert Joint. Under the Details, select the connection type to be body ground and type to be general. We want all the translations and rotations in all directions to be free, so set all of them to free. Under Mobile, select the outer faces of the spacer again. Now we've defined all the connections required for the different components to interact with each other. The next item on the tree outline is Mesh. Right-click on Mesh and choose Generate Mesh. The next thing we need to do is define the loads and boundary conditions for our simulation. We will have 2 steps in our simulation. In the first step, the rotational velocity of the yo-yo ramps up from 0 and reaches a specified value, similar to what happens when we throw a yo-yo from rest. In the second step, we just let the yo-yo rotate for a considerable amount of time to see how it behaves. So first let's define the 2 steps and set parameters for numerical calculations in the analysis settings. In the step control, we define the number of steps to be 2. Let's say the first lasts for 0.5 seconds and the second step is 10 seconds long. So let the current step number be 1 and set the end time to be 0.5 seconds. We set auto time stepping to on so that the solver can adjust the time steps it takes. Next, let's define the second time step. So now the current step number is 2 and the step end time is 10 seconds. Again, the auto time stepping is on with a minimum and maximum time step as shown here. Since the simulation could take very small time steps, and we have a time step of 10 seconds, we do not necessarily want to store results at all time points since that could occupy a lot more storage space and take longer to post-process. So let's go to Output Controls under Store Results at, select Equally Spaced Points, and input a value as shown. The first load acting on the yo-yo is its weight, which is constant throughout the simulation. To simulate this, right-click on Transient, insert Standard Earth Gravity. By default, gravity acts in the -z direction, and we will leave it as is for the simulation. In the tabular data, we see that this remains constant in both the steps. Next, we want to simulate spinning of the yo-yo. We do this by applying a rotational velocity to the general joint that we defined between the spacer and the ground. So right-click on Transient, insert Joint Load. In the Details window under Scope, choose the general joint. We can see the local coordinate system for this general joint. In terms of this local coordinate system, the yo-yo spins about the z-axis. So, in the definition under degree of freedom, DOF, choose rotation z. In the type, select rotational velocity, and under magnitude, select tabular data. At the bottom right corner, change the units of rotational velocity to RPM. In the tabular data, input a value of 5,000 RPM at time 0.5. So now the rotational velocity will ramp up from 0 to 5,000 RPM in 0.5 seconds, and this simulates the launching of the yo-yo. In the second step, we do not want to force the yo-yo to spin at this speed, but instead let it spin freely as the physics of the problem dictates. So we deactivate this boundary condition in step 2 by right-clicking on the corresponding cell in tabular data and choose Activate Deactivate at this step. Now the simulation setup is complete. So right-click on Solution and choose Solve. The solver has finished computing the solution, so it's time to visualize the results and see how the yo-yo performs. To see how the yo-yo moves, right-click on Solution, insert Deformation Total, then right-click on Total Deformation and choose Evaluate All Results. Let's set the animation time to 10 seconds and use 100 frames. If we animate the total deformation, we can see that the yo-yo wobbles quite a bit while spinning. In order to quantify this wobble, let's look at the motion of the spacer. So, right-click on Solution, insert Probe, Joint. In the details for the boundary condition, choose the general joint. In the result type, choose Relative Displacement. Again, right-click on the joint probe and choose Evaluate All Results. Select the spacer under Geometry, right-click, and choose Hide All Other Bodies. Now, when we animate the joint probe, we can see how the spacer wobbles. To quantify this wobble, let's look at the rotation of the spacer. So, right-click on the joint probe and choose Duplicate Without Results. In the second joint probe, change the results type to Relative Rotation. Now, right-click on the joint probe and choose Evaluate All Results. Ideally, the spacer should have rotation only about the local z-axis and have zero rotation about the local x and y axes. But here we see that the spacer has a non-zero rotation about the local x and y axes. So let's discuss a bit of this case. The center of mass is on the spinning axis and aligned with the string, but one of the principal axes of inertia no longer aligns with the spin axis. Consider a yo-yo which has a geometry as shown here. The case we just discussed could be represented by offsetting the two protrusions on the yo-yo in opposite directions. It can be visualized if we think of our yo-yo in terms of two halves. One half will have its center of mass on one side of the spin axis, and the other half on the other side of the spin axis. One principal axis of inertia of the entire yo-yo will no longer align with the spin axis. A simple way to think of why this is an issue is the protrusion on each half causing a rotational imbalance. Our yo-yo has an unbalanced force acting radially outward and is equal to the unbalanced mass, in this case each protrusion, times omega squared, times the radius to the protrusion. The forces are acting in opposite direction. This causes a moment to be generated that rotates with the spinning yo-yo. The result of this will be a wobble of the yo-yo, which we clearly saw in the simulation. A more complex yo-yo design may not have a simple feature like our protrusion, but rather a complex mass distribution that results in the misalignment of a principal axis of inertia from the spin axis. One would typically want to change the mass distribution so a principal axis of inertia is aligned with the spin axis. So let's alter the yo-yo design to reduce the wobble. To do this, go back to Workbench, right-click on Geometry cell and select Edit Geometry in SpaceClaim. This opens the CAD model in SpaceClaim. Now, select the entire geometry, go to Measure tab, and click on Mass Properties. We see that the center of volume is 0, 0, 0. In other words, it's aligned with the string direction, but the principal axes of inertia are not parallel to the spin axis. This was causing the wobble. Keep in mind that since we have not set a material on any of the bodies in SpaceClaim, it reports properties based on volume, not mass. If your design has materials with varying density, the material can be assigned to each part, and then the mass properties output will reflect that. But in Ansys Mechanical, we've already specified the materials, so the simulation will account for variations in density. Let's get back to our yo-yo and try and remove the wobble. On the left, we see that the yo-yo geometry is composed of a left and a right side and a spacer that connects the two halves. If we click on the tiny arrow next to right, it expands further, and we can see the right side is composed of a cover, a body, and a snap ring. Let's rotate the cover to change the location of the protrusion. Select Cover on the tree, then on the Sketch tab, pick Move. A triad appears on the cover. Select the curve arrow indicating rotation about the x-axis and drag it. Now enter 180 in the activated field and press Enter. We now see that the two protrusions are now offset from the spin axis in the same direction. Again, select the system on the left, go to the Measure tab, and click on Mass Properties. We now see that the center of volume is now slightly offset from the spin axis, but a principal axis of inertia is more aligned with the spin axis. Intuitively, this offset of the center of volume might seem like an issue. So let's see if our intuition is correct by repeating the simulation with this new geometry. Now return to Workbench, right-click on the model, and refresh, then open Mechanical. We'll now solve this case. When we animate the total deformation, we see that this design of the yo-yo is fairly stable and does not wobble. When we animate the results for relative rotation, we see that the spacer, and hence the yo-yo, has an almost zero rotation about the local x and y axes. So by performing the simulation, we can see that the results are somewhat non-intuitive. Although the yo-yo design is not axisymmetric, it is still a fairly stable configuration with a bit of oscillation, but at least no wobble. For a larger imbalance, the oscillation may be more significant and no longer acceptable. So let's discuss a bit this case of our rotating imbalance. Our first case, when the principal axes of inertia were not aligned with the spin axis, we had a rotating imbalance. But in this case, the imbalance force from each half acts in the same direction, not imparting a moment, so no wobble. But since the yo-yo is spinning, the direction of these forces is oscillatory in nature and will still excite the yo-yo in the in-plane direction normal to the spinning axis. The effect, as we saw in the simulation, is a yo-yo that has a bit of in-plane oscillation and a spin that's not as smooth as when the center of mass lies on the spin axis. Lastly, let's see what happens if one half of the yo-yo was offset along the spin axis by some amount. This can represent manufacturing inaccuracies or even an issue in the assembly of the yo-yo. We can do this in SpaceClaim, but just to show you a different way, we use Part Transform in Mechanical. Right-click on Model and choose Part Transform. Now click Control and select the three components that make up the right half and click Apply. Under Definition, define Translate X field to be 2 millimeters. Now, right-click on Part Transform and choose Transform. The right half of the yo-yo has now been offset. Let's rerun this model. Now when we animate the total deformation, we see that after a few seconds, the yo-yo starts to rotate about an axis normal to its spin axis. This is called gyroscopic precession. It happens because the spinning of the yo-yo and the moment from the gravitational force result in a gyroscopic moment that causes the yo-yo to twist about the string. We welcome you to experiment further with your own design. And of course, if trying to have the smoothest spin to your yo-yo, you will want the center of mass to coincide with the spin axis, also aligned with the string, and one principal axis of inertia aligned with the spin axis so there is no imbalance. Keep in mind that there may be some initial oscillation when the yo-yo initially stretches the string under the force of gravity. Then the yo-yo continues to spin with decreasing oscillations, and this dynamic behavior can be governed by changing the stiffness and damping of the spring, which represents our string. Now that we have simulated 3 different designs of the yo-yo, we can see how simulations can help improve and optimize product designs before manufacturing. Simulation can also provide insight into non-intuitive behavior, such as in the case of the second design, which, though not axisymmetric, is still a fairly stable design. We can also simulate the behavior of the yo-yo at different RPMs, including damping loss about the spin axis to simulate friction of the string or many other loading conditions. If you find this video helpful, please like, comment, and subscribe. To find other interesting topics, please check out our channel for more videos and visit ansys.com/courses today.